Hi everyone, welcome back to the Technion CCE Deep Learning course. I'm Tal, and in the second part of the recap tutorial, we are going to cover algorithms that are based on a single neuron, which is based on the linear combination we saw in linear regression. These algorithms include the Perceptron, Logistic Regression, and Softmax Regression. We will also get a first taste of PyTorch by implementing a simple logistic regression. Finally, we will close this part with a brief overview of activation functions, which are a core component of neural networks that are composed of multiple neurons. So let's begin. Okay. So before we dive in, I want to let you know that sometimes we are going to use external packages that we can easily install directly in our notebooks or on Colab. You can see an example here for the package TorchViz. TorchViz helps us illustrate or plot the structure of the computational graph of neural networks in PyTorch. And it's just a nice tool to have. It's not mandatory, but you can use it if you want. Okay, so let's begin with discussing the family of discriminative models. And discriminative models are a class of models that are used in statistical classification, especially in supervised machine learning, which is what we do here. Now, a discriminative classifier tries to build a model just by depending on the observed data or the features, while learning how to do the classification from the given label. So our annotations or all labels, right? So compared to another family called generative models, discriminative models makes fewer assumptions on the distributions, but like all machine learning models, they depend heavily on the quality of the data. So if you want the best model you can get, you should also have the best data you can get. So for example, given a set of labeled pictures of dog and a rabbit, or usually dogs and cats, the input features are going to be pixels. So these discriminative models will be matching a new unlabeled picture to the most similar labeled picture and then give out the label class, a dog or a rabbit, right? And typical algorithms approaches include logistic regression, support vector machines, and other models. So we begin with the classic algorithm, which is one of the first and simplest linear model, which is based on a single neuron, which is called the Perceptron. And what we're going to do here is we're going to use this linear combination we saw earlier for linear regression, but we are not using it directly, but we have another step, which we do. So based on a linear threshold unit, LTU, the input and output are numbers, not binary values, and each connection is associated with a weight. Now, this idea is inspired by biological neurons. I'll talk about it in a bit, but it's not really how the brain works, so keep that in mind. So the LTU, the linear threshold unit, computes a weighted sum of the input. So just the linear combination we saw earlier for linear regression, and basically we are going to initialize some set of parameters, W or theta, and we're just going to do this linear combination with our input features X to get some value Z, right? Now, in linear regression, we took directly this Z to regress the output, but here we are doing classification. So we are going to apply a function, which is in this case going to be the step function, over the sum, and predict the results, which is going to be a boundary. So if it's above some value, then we classify it as one class, and if it's below this threshold value, then we classify it as the second class. So binary classification. Now, the most common step function used is the Heaviside function, but sometimes also the sign function is used. So if we take the sign function over this Z, then our labels are going to be +1 or -1. And the perceptron is illustrated right here. So we have the input features x1 to xn. And for each feature, we have the corresponding weight, W1 to Wn. And of course, we have the intercept or bias term, which is constant 1, and it is assigned the W0 parameter. We then take the linear combination and then apply the step function. The output is predicted using the sign function or some other step function. Now, training of this perceptron is very similar to stochastic gradient descent. We'll talk about it in a bit, but it's a very old idea which draws inspiration from biological neurons. So the connection weight between two neurons is increased whenever they have the same output, so if they agree on the output, and otherwise it's decreased, right? And basically we measure the error and update the weights according to this error. Now, it is just inspired by biological neurons. The brain does not really work like this, and it's probably more complex than what we present here. So at each iteration, the perceptron is fed with one training instance and makes a prediction for it. So just like stochastic gradient descent, so we're not working on batches, we are going to go over sample by sample, so just like a batch size of 1. And for every output that produced the wrong prediction, it reinforces the connection weight from the input that would have contributed to the correct prediction. And the criterion is described here. So basically we measure the error over our data, so WTX, and compare it with the ground truth label. And the learning rule, or the weight update, goes as follows. So WT plus 1 equals to the previous WT plus some step size eta multiplied by the ground truth label yi minus sine WT T transpose xi. So this is just the linear combination and the sign over it. And I'll just mention that the labels are +1 or -1. And similarly to linear regression, we still have the feature weight here, the feature value here, xi. Now let's try to spell it out. So we have yi. So for example, if it's the positive class, then we have +1 here. If the model outputs something positive, then the sign would be 1. So this term here goes to 0, and there is no update. So if in the current iteration, the current model parameters agree with the ground truth label, so basically the correct output is like in the ground truth label, then there is no need to update. Okay. Otherwise, if they don't agree, so for example, if the ground truth label is 1 and the output is -1, then we actually have here 2 multiplied by the feature value, right? And of course, we can have it in the other direction, so -2 in the opposite direction. So basically, there is an update only when we are wrong. Okay. So the decision boundary that is learned is, of course, linear, and the perceptron is incapable of learning complex patterns such as the XOR problem, right? And we have an hyperparameter here, which is eta, the learning rate or the step size. Now we have some nice theory for the perceptron for the very simple cases. So the perceptron convergence theorem states that if the training instances are linearly separable, then the algorithm would converge to a solution. And there can be multiple solutions, multiple hyperplanes. There is no guarantee where we will stop. If the data is separable, then we can get 100% accuracy, and there can be many planes that satisfy this. So if we take a look at what happens here, then we can see that the perceptrons actually do not output a class probability. So there is no notion of confidence in terms of probability. They just make prediction based on a hard threshold, but we can get some notion of confidence by looking at the magnitude of the dot product, right? So by looking at this dot product, we can get some similarity measures. So if it's very high or very large, then there is some notion for the model that it is confident that it belongs to the positive class, right? And of course, the same for the negative part. So let's take a look at the pseudocode. So we need to initialize some learning rate and some parameter vector, right, W. And we have we have a parameter for each feature. And then we are going to go over over the entire data, sample by sample, just like SGD. And then we are going to apply this update rule here, right? And when do we stop? So stopping criterion can be a maximal number of iterations. It can be some change in the error, can be the number of updates to the weight, anything you want. But at some point you'll stop. You need to. So if your data is linearly separable, then your stopping criterion, which is based on error, will probably be satisfied. Otherwise, you need to stop it sometimes. So a maximal number of iteration is a very common stopping criterion. Let's take a quick look at what does it mean that we can have multiple hyperplanes. So we can see that in this case, the data is linearly separable. And there can be many hyperplanes that satisfy this, that get 100% accuracy, right? So which hyperplane should we pick? So the model picks one based on your initialization of the parameter vector and your stopping criterion, of course, right? So there can be multiple planes. So we are just guaranteed to converge. There is no guarantee to which kind of to what kind of or what type of hyperplane. There are other algorithms like SVM that need to satisfy some constraint and then like the maximum margin, and then we get usually the same output, the same predictor. Okay, so let's load the breast cancer data from before, right? The same one, nothing is different. We're going to do classification. So now we are going to take the radius mean features and the texture mean features, and we are going to try to predict from them the class, right? So we are shuffling our data. Of course, we are scaling. Again, remember, we are using only the train set to fit the parameters of the scalar. So in this case, standard scalar, so mu and sigma. And then we transform the train and test data. We now take the perceptron from Scikit-learn and give it a maximum iteration of 1000. We then fit and predict the accuracy, and you can see that the accuracy is around 85%, which is nice, right? And we can also plot the diffusion boundary and see what the perceptron is learned. So here you can see a plot of the samples, right? And we have in green our learned plane from the perceptron. And you can see that it shows, so the first thing you should notice is that the data is not linearly separable. So we can't find a plane that separates the train set with 100% accuracy. That's okay. Most of the data most of the data sets are not linearly separable. But you can see that it stops somewhere. We can maybe, if we would have let it run a bit more, the plane would have been different. And maybe if you were yourself to draw the separating plane, maybe you would put it somewhere else, right? So for example, I would put it like somewhere like here, right? Seems like a more reasonable choice. But this is the perceptron. A very simple model, which works nicely. One of the classic and earlier models that apply the idea of using a linear combination of a single neuron and just some activation function, in this case a step function. Okay, now we are going to talk about another algorithm which is based on a single neuron, which is called logistic regression. And I want to drive this discussion from the maximum likelihood perspective. So if you recall, in the previous tutorial, we discussed how we derive for linear regression, how we derive the MSE, the mean squared error, from the maximum likelihood estimation objective function. And we assume there that our data is actually comes from deterministic function theta tx. However, since we sample from the real world, then we have some added noise, and this noise, this epsilon, is actually distributed like a white noise, so it's normal with zero mean and some variance sigma squared. And we saw that when we assume this kind of distributions, then minimizing the negative log likelihood results in the mean squared error, the MSE, right? And minimizing the NLL is the same as maximizing just the likelihood itself, which is exactly maximum likelihood estimation. So when we assume that the data is created in a different way, we get different loss functions, as well as, and we will now demonstrate the idea with the Bernoulli distribution. So this is just a recap of how we derived for the Gaussian assumption. So you can see the actual equations here, and we just converge to the MSE. Now let's take let's shift the talk to classification. So so far we derived this for linear regression. We try to regress some values, but now we actually care about classification. So we actually want to output a class, right? So a prediction of classification. And we also want to add some perspective or some notion of probability, of some confidence. So this is why we're going to use some function called the sigmoid function, also called the logistic function, and it's denoted as sigma of x, and you can see it right here. And the nice thing about the sigmoid function, you can see it right here, that it is continuous, and it's bounded between 0 and 1, which aligns exactly with what we want. So we want the output of the network to be some confidence or some probability of the input sample to belong to the positive class or to the negative class. So the higher the probability is to 1, then the model is confident that the input sample belongs to class number 1. Exactly what we want. So the idea is that we are going to take this linear combination WTX or theta TX, and then instead of applying a step function like we did in Perceptron, we are going just to apply the logistic function and add and get a probability. Cool. So very same idea, right? However, now we are going to derive this from so we need to train it with some loss function. We are going to derive it from the perspective of maximum likelihood estimation. And notice that when we talk about binary classification, then you have 0 or 1, right? Like class 0 and class 1. And we can think about it from the perspective of Bernoulli distribution. So just like a coin flip or coin toss, right? We are going to model the output, the label, and the conditional probability, P of y given x parameterized, and the model is parameterized by theta, right? So just this likelihood. And the likelihood is modeled by the Bernoulli distribution because Bernoulli distribution is just a coin toss, so 0 or 1. And in this case, we are going to use the parameters of the distribution are not mu and sigma, but just the p, the probability of the sample being classified as 1. Okay, and the way we are going to do this is by applying the sigmoid function over theta tx, over our output of the network, or output of the single neuron. So if we write down the probability function, then the probability function of the Bernoulli distribution is p to the power of y multiplied by 1 minus p to the power of 1 minus y, and p is a value between 0 and 1, and we parameterize p by the sigmoid over theta tx. Nice. Now we are going to use the following notations. You can see them right here. So if the output of the sigmoid is closer to 1, then we want, hopefully this belongs to the label of yi equals 1, and otherwise it's 0. Okay, so logistic regression, this is the idea, right? So it's called, it has regression in its name, but we actually doing classification. So some regression algorithm can be used for classification as well, depending on the output activations. In this case, the sigmoid. So logistic regression is commonly used to estimate the probability that an instance belongs to a particular class. And typically, if the estimated probability is greater than 50%, then the model predicts that the instance belongs to that class. So class number 1, also called the positive class, or anything you want to call it. And else it predicts that it does not, so it's just a binary classifier. So if it's below 50%, then it's closer to 0, then the class should be 0. So how do we estimate probabilities? So very similarly to linear regression, a logistic regression model computes the weighted sum of the input features with a bias or intercept term. But unlike linear regression, we don't take directly this value. We actually apply an activation function called the logistic function, and we get a number between 0 and 1. But how do we train this model, right? It's not that trivial. So we're going to do the same derivation that we did for the MLE for the linear regression case, but now we're going to assume the Bernoulli distribution, and we're going to take the same identical steps. So the objective of training is to set the parameter vector theta or w so that the model estimates high probabilities for positive instances, like for y, the ground truth label y equals 1, and low probabilities for negative instances y equals 0. So we want to pull the prediction of positive samples to 1 and otherwise to 0. So let's take a look at it from the perspective of likelihood estimation, right? So we want to maximize the value, the label y, given our input feature x, and our model is parameterized by theta. Now we are going to assume that this likelihood is a Bernoulli distribution, and we are going just to set the and put all the input parameters just like the Bernoulli distribution, which is right here. Right? So we just plug in all the variables. In this case, our p is modeled by the sigmoid over theta t of x. You can see it right here. And basically, we get this loss function, which is also called the logistic regression cost function, or otherwise binary cross entropy. So you can see it right here. And I want to give a bit of motivation or intuition what this function is doing, right? So let's talk about the logarithm function. So let's take a look at minus log t, which is apparent right here. You can see it right here. So what happens to this term? So when the input of the log function t approaches 0, then log goes to minus infinity. And since we have minus infinity, so minus over minus infinity is just plus infinity. So in the case where our current sample is labeled as 1, then you can see that the loss function resorts to being 1 multiplied by log of pi I1, which is just the logistic function, right? And we have this minus here, and this part is eliminated because it's just 0. So the loss function is minus log of sigmoid of theta t xi. So in this case, if your prediction goes to 0, then the cost function will be very large, and at the limit it goes to infinity. So if the model estimates a probability close to 0 for a positive instance, then the loss function will be large, and we want to minimize it, right? And of course, if the estimated probability is close to 1 for a negative instance, we get the other direction, and it will also be very large. On the other end, when minus log t is close to 0 when t is closer to 1, so the cost function will be close to 0 if the estimated probability is close to 0 for the negative instance or close to 1 for the positive instance. So basically, if your model outputs something which is very closer to 1, then log of 1 is 0, so the loss function will go to 0, which is what we want, right? So this is why it's called binary cross entropy, right? And the nice thing about it is that the cost function in the case of logistic regression in the single neuron case is convex, and we can optimize it with gradient descent. It does not have a closed form solution like in linear regression, but luckily gradient descent works pretty well here. So we can take the logistic regression directly from Scikit-learn, and we can do the same process like we did for the Perceptron, and you can see that the accuracy is much better, so around 90%. And when we plot it, we can see that it learns a plane which is a bit different from the one that the Perceptron learned, but that's okay because it led to a better accuracy. And I guess it's a good, like, if I were to put the decision boundary somewhere, this is a good place. Okay, so this is logistic regression. We saw how it is connected to the MLE when we assume that we have Bernoulli distribution, and we can nicely derive the loss function, which is binary cross entropy, which is quite popular in machine learning and deep learning when we have binary classification. Now, what we're going to do now is get familiar or get a little taste of PyTorch. And don't worry, everything you're going to see here in PyTorch, we are going to dive much deeper later in the course. And these things will return a bit later as well. So don't worry, we are going to go over this a couple of times, but it's a good spot to start talking about it. So we will see a general recipe for building neural networks in PyTorch. In this case, we don't have a neural network, we just have a single neuron, which is just a single layer, right? And here it is. This is the entire implementation of the single neuron. It's quite short, but let's try to understand what happens here. So in PyTorch, all neural network models, no matter how complex or how simple they are, they inherit from a parent class and an dot module, right? And this enables us a couple of functionalities that we will use to train the models. Now, when you inherit from NN.model, you must implement two functions, two methods, the init function, the init method, and the forward method. And we'll now explain what happens in each method, and it's quite simple, and these steps will return later when we implement more complex networks. So in the initialization function, the init method, we initialize the parameters of the neural network. So the number of parameters, such as the number of hidden layers, units, types of layers, and etc. In our case, we only have a single layer and an activation function, which is a sigmoid. So we can see here that one of the layers, which is an instance of a linear layer, is going to be called fully connected, or FC in short. And it's just a linear layer that maps from the input features to 1, because we have a single neuron that takes in the features and output the probability, right? Now, this is calculating the theta tx or wtx, right? So just the linear combination. Now we're going to apply some activation function, in this case the sigmoid, which outputs a number between 0 and 1. That's it. Now for the forward function, we actually implement the forward pass of the network. So what happens to the input? So in the initialization function, we define the basic blocks, the Lego blocks of the network, the layers, and everything that we defined before we do the forward pass. And in the forward pass, we actually define what happens to the input x using these basic blocks. So the idea is that we are going to define the order in which x go through all the blocks we defined in the initialization functions. In this case, we have x, it first goes through the linear combination layer, so the fully connected layer, and then we apply a sigmoid function over it. So without the comments, it will be much shorter, right? So a couple of lines of code. And basically, this is what we are going to do for every kind of neural network, as complex as they are. So now that we have our network, we need to train it. And here is a general recipe for training in PyTorch. You will see that this recipe will come up again and again in the tutorials, and basically things are more or like the same. So the idea is that we're going to define some stuff that are relevant to any neural network training, but the only difference is going to be the instance of the model itself. In this case, we're going to use our single neuron from above. So the first thing we usually do is we define the device on which we're going to run the calculations. So in this case, we can use the CPU, or if we have an NVIDIA powered GPU, we can use the CUDA device. So this is just a GPU. And this lines automatically checks whether you have it available, whether you have the drivers for CUDA available. And if so, then this line will pick the GPU, and otherwise it will resort to the CPU. Now it is important to define this device at the top of the code, because we want our training scripts to be agnostic to the type of device. Because if you want to transfer your code to your friend and your friend doesn't have a GPU, then you don't want your code to fail because you tried to send all the variables to a device that does not exist. So if this lines automatically picks the device, then it's agnostic, because now we are just going to use the device as a general device, not something super specific. So what we're going to do is we're going to create an instance of our model, so single neuron. We need to provide it with a number of features, and because this is how we defined the first or the only linear layer in our model. And then what we do, we send it to the device. So if the device is GPU, then the model will be transferred from the CPU to the GPU, and otherwise it will remain on the CPU. Then we need to define the step size or the learning rate, and in our case we are going to use stochastic gradient descent to optimize the parameters of the model, and later in the course we will meet many more optimizers that are all mostly based on gradient descent. Now the optimizer takes in two inputs. The first one is the parameters of the model. So every network that inherits from NN.model, you can just access all the parameters, no matter how complex the model is, by calling model.parameters, and this will return a generator for all the parameters of the model, no matter how complex the model is. And the second input is the learning rate or the step size, and of course it's a hyperparameter that you should tune. Some optimizers have more hyperparameters like the momentum and other kind of hyperparameters. We will talk about them later in the course. We also define the number of epochs, the number of iterations we are going to do over the entire dataset. We need to define our loss function, our objective functions, in this case binary cross entropy, no surprise here. We also, of course, scale the data, gradient descent based algorithm. They like scale data. And our training loop, which is very short, is going to be pretty much the same every time. We are going to have an external loop for the number of epochs, the number of iterations we are going to go over the entire dataset. Usually we will have an inner loop that goes over the batches. In this case, we are just doing batch gradient descent. We just take the gradient step over the entire data because we don't have a lot of it. So just 500 examples, around about 500 examples. So that's not very hard, not very heavy to compute. So we have our features and our labels. Pay attention that we need to place them on the device. So the device is picked automatically, so that's good, that's agnostic. Next, what we do is we do the forward pass, we give our model the features, and we get the output predictions. Now, when you do this model features, this calls to the forward function. And this is why we must implement the forward function, because if you want this to work, this line to work, then you must implement the forward function, right? So this just calls the forward function. The next thing we do is we calculate the loss function. So we have the labels, the ground truth labels, and we have the predictions from the network. And in this case, the binary cross entropy, we just calculate the values. Now we are going to do the actual update. And to do the actual update, we have 3 lines that are always come in the same order. So the first thing we do is we clean or clear the gradients from the previous iterations. So when you use PyTorch, and you calculate gradients, then these gradients are stored in the tensors field called .grad. So you can access the .grad field of the inputs, and you can see the actual gradient. And if you don't zero it out between iterations, then it will just accumulate, right? So if in the previous iteration the gradient value for some feature was 1.5, and now you in the consecutive iteration the gradient was 0.3, then if you don't call zero grad, then the gradients accumulate, so it's 1.5 plus 0.3, then the gradient will be 1.8, and you usually don't want it. There are some cases where you do want to accumulate gradients, but usually it's not the case. So we want to zero it out between iterations. The next step would be actually the calculation of the gradients of the loss with respect to the parameters. So we just call loss.backward, and this will actually assign the grad field for each parameter. And then we actually need to do the update step. So we need to apply the update rule, and we do this by calling optimizer.steps. So optimizer.step will go over the .grad fields and just apply the update rule, and it depends on the optimizer you're using. So each optimizer has its own update rule. So in SGG, we are familiar with the update rule, and it just applies it. We can print what happens, so we can see that the loss goes down and it plateaus at some point, and we can also check the accuracy and see that we reach the same accuracy. Very nice, all is good. Okay, now we are going to use some nice feature of PyTorch, and we can actually take a look at the computational graph. So we can use the library we installed previously called TorchViz, and it will take your model and plot or show you the computational graph and show you what happened when you input some sample inside the network. So what happens to this x? So as you can see, it is multiplied by this w, so fc.weight, right? And then we add a bias, and then we apply sigmoid over it. So this is exactly what we describe in code in the forward function, but we can also see it in a graph, which is nice. So this covers binary cross entropy with logistic regression. But what happens when we have more than 2 labels? Then we move on from binary to multi-class or multinomial logistic regression, which is also called Softmax Regression. Now the idea is not that different, and basically we can generalize the logistic regression idea to multiple classes. And given an instance X, the Softmax regression model first computes a score Sk for each class K, So we're going to have a set of parameters for each class, right? And then we're going to estimate the probability for each class by applying the softmax function, which is normalized exponential, to the scores. So let's say we have 10 classes, then we are going to initialize 10 sets of parameters. And then for each instance, we are going to multiply it by the parameters of each class and get a score for each class. And of course, we want to maximize the score of the correct class from the ground truth labels. So each class has its own dedicated parameter vector theta k, which is usually stored in a row of a parameter matrix big theta, so capital theta. And the softmax function just turns the scores into normalized probabilities. So the softmax function takes the exponential over the score and normalizes it by the sum of all the exponentials for all the classes, right? So you will get, for each class, you get some probability function. Now, basically at inference time, you don't need to calculate the actual probability. You can actually just take the argmax, right? So no need to calculate the actual probability. And the loss function is very similar to the binary cross entropy. You can see it here. It's called cross entropy. And in this case, we are just trying to maximize. So the y's are going to be a one-hot vector, where we have one in the cell corresponding to the correct class, and then we optimize the output of the network for this class. So if you have a sample that came from class number 3, then all of these terms are going to be 0 except for k equals 3, and you want the output for the set of weights for class number 3 to output a probability which is closer to 1. When k equals 2, then we resort back to the binary cross entropy. And you can take a look at the derivative of the loss function, and you can use it directly from Scikit-learn just by using multi-class input. And of course, you can add the regularization term C, which is very similar to what we talked about in linear regression. So that's it. We will see a lot of cross entropy and binary cross entropy in this course. So just keep in mind how we utilize softmax and how we utilize the sigmoid function. But we are going to have all these functions already prepared for us in PyTorch, so we just need to import them and apply them over our outputs of the network. We are now going to close this tutorial with some preparation for the deep learning part. And we're going to talk about just shortly about activation functions. We will dive into that much deeper later in the course, but let's just give you a taste of what is to come. So one of the key changes that made to the Perceptron that brought upon the era of deep learning is the addition of activation functions. And we are going to activate the output of each neuron. And we are going to have a lot of neurons stacked in multiple layers. Now, what this enables us is this allow to learning of nonlinear function. And this will help us solve cases where the data is not linearly separable, and we are going to use a nonlinear decision boundary, so something much more complex. So some examples for activation functions. So this is just a list of 3 activation functions, and we will see many of them, many more of them later in the course. So the first one we already met, and the sigmoid. It outputs value between 0 and 1, which can be used for binary classification or just as a probability estimation. Second one is called hyperbolic tangent functions, or tanh. And the output is between -1 and 1, and this tends to make each layer's output more or less normalized at the beginning of training, and this can help speed up convergence sometimes. We don't use it inside the network, and today we have other activation functions, but there are some types of layers, for example, a recurrent layer, which we'll talk about which we'll discuss when we get to the recurrent neural networks part, when we talk about time series. And this using the hyperbolic tangent function helps us have a numerically more stable optimization. Another activation function, which is super popular and super simple, it's called the ReLU function, so rectified linear unit, and it's very simple. It's just taking the maximum between 0 and the input. So if your layer output, if you have a linear layer and the output is z equals w(tx), and then when you apply ReLU, just take the maximum between 0 and z. So it's a continuous function. It's not differentiable at zero at z equals 0. However, it is the most common activation function, as it is fast to compute, and it does not bound the output, which helps with some issues happening during gradient descent, discussed later in the course. You can see a plot of the activation functions here and their derivative. So we will need the derivative of the loss of the activations in order to calculate the update to the parameters, and we will see later in the course how it all adds up. Okay, so here we have some more videos if you want to dive deeper into the algorithms covered in this tutorial, and if you want to read more, there is a recommended reading right here. Thank you for watching, and I will see you next time.